Hi, my name is Jacqueline Pereira from Mountain House, California, and my project is Cycloplast, upcycling fish scale waste as an environmentally friendly, thin, plastic-like material to combat wet pollution. We are addicted to plastics. Not a day goes by without us using them. And now we are drowning in it. And the biggest bad guy is the thin plastic bag, with an average working life of 15 minutes. And by 2050, plastic will outnumber fish in the ocean. Speaking of fish, 30 to 70% of a fish is wasted, including fish scales, an inedible byproduct of fish with little to no value at all. Now, people may think, once a waste, always a waste, but I see this fish scale waste as an untapped resource. Interestingly, fish scales are a type of dermal bone and are strong yet thin and flexible just like plastics, but unlike plastics, they can degrade naturally. So you may be wondering, what does this fish scale waste have to do with plastics? Here's my thought process. If collagen is a matrix polymer and the main structural protein in animals, and type 1 collagen in fish scales has a tensile strength stronger than steel, then, using the concept of structure, I can isolate the collagenous fibrils and reconstitute the collagenous matrix to develop an alternate material to thin film plastics that I call cycloplasts. And this is what my project is all about. So I developed this using 3 species of freshwater fish scales, Nile tilapia, mangrove red snapper, and giant gourami. And I conducted 5 main stages of development. Preliminary, to determine optimal pretreatment conditions. Pretreatment, to isolate the intact collagenous matrix through deproteinization and demineralization. Extraction, to form a thin film matrix. Cooling/drying in my custom cooling chamber to accelerate formation. And thermal dehydration, to enhance the physical properties by removing water molecules and forming thermal bridges. And it conducted 3 main phases of testing: protein analysis with Bradford assay and protein electrophoresis, physical testing with tensile strength, shrinkage, and transparency, and environmental testing with phytotoxicity and degradation in soil and hydroponic environments. So here's a collection of images from my development stages, as well as my tensile strength testing in the bottom right. You can see the steps I took in the formation of cycloplasts, as well as me testing the maximum force using digital force gauge on my samples at the bottom, which I then divided by cross-sectional area to yield tensile strength based on ASTM D882 for thin film plastics. And here's some images from my protein analysis on the left with Bradford assay and protein electrophoresis, as well as some samples ready for testing on the right. And here are my images for environmental testing with lettuce seeds in hydroponics to simulate aquatic degradation, phytotoxicity, and water solubility. Lentil beans in soil to simulate terrestrial degradation, phytotoxicity, and home composting potential, as well as lentil beans in other mediums to further demonstrate the lack of phytotoxicity. And I tested 59 plants total over a period of 6 weeks. And after 9 months and hundreds of trials, my results are promising. I successfully upcycled fish scale waste with a 93% yield into a thin, translucent, plastic-like film, reaching tensile strengths up to 53.77 newtons per millimeter square. The optimal extraction temperature was at 55 degrees Celsius, where tensile strength peaked, and thermal dehydration was proven to boost tensile strength up to 68%. Cycloplast also had higher shrinkage performance from 130 to 150 degrees Celsius, whereas LDPE melted and deformed. This is because cycloplast is primarily protein, which does not melt, shrink, or deform at these temperatures, especially in the absence of water due to thermal dehydration. And as temperatures increased, transparency also decreased from 74 to 25.8%. Protein analysis gave me insights into the relationship between the extraction conditions and the physical properties. Increasing extraction temperature increased the protein concentration, although it decreased the molecular weight, potentially reducing the tensile strength. Interestingly, there was an anomaly with the red snapper scales at 55 degrees Celsius extraction, where the concentration was lower than expected, although still following the trend. This is possibly because red snapper lives in a brackish environment and therefore contains more calcium salts in its scales, and that means it requires higher temperatures to extract higher concentrations. Cycloplast fully degraded within 4 to 5 weeks in both soil and hydroponic environments. with a 100% seedling survival rate and no signs of phytotoxicity, including chlorosis, necrosis, and wilting. Plant growth varied between 8% less than control in hydroponics to 4% higher in soil. And this is possibly because, in hydroponics, the dissolved protein may reduce the water's dissolved oxygen capacity, whereas in soil, microorganisms can break down cycloplasm into its amino acids, allowing it to enhance plant growth. So in this project, I made 4 key discoveries. Number 1, the intact collagenous matrix is the main determinant of tensile strength, and its properties are influenced by the pretreatment, extraction, and thermal dehydration conditions. Number 2, thermal dehydration is proven to boost tensile strength by removing water molecules and forming thermal bridges. And my custom cooling chamber is proven to accelerate formation by accelerating the transition from disorder to order. Number 3, cycloplasm's degradability is due to its composition being almost 100% protein, which microorganisms can then break down into amino acids. And number 4, I successfully developed critical parameters for successful formation in real-world applications. And speaking of applications, since one size does not fit all, Cycloplast is targeting thin film plastics that we use and throw away most often. And my prototypes, which can easily carry 15 pounds, are ready to be smarter options for road applications. With a cost of $3 a kilogram, this is cost competitive. And think about the benefit to the environment. In fact, it has been my passion for the past 4 years to develop alternate materials to plastic from various wastes, and Cycloplast shows the most promising results yet. Let's take a look. So yes, there may be no magic bullet to the plastic problem, but this is exactly why Cycloplast is important. It can eliminate the need for a cleanup by naturally degrading in both soil and water, and with a tensile strength comparable to regular plastics, it can prevent any additional plastic pollution from accumulating. By upcycling fish scale waste, we can begin to live our lives plastic-free. Here are my references. And I'd like to thank my school, teachers, and family for supporting me on this journey. I'd also like to thank the JSHS organization and all the organizers for giving me this opportunity. I'd also like to thank you, the listener, for taking the time to listen to my presentation. Thank you.
Hello, I'm Brian Minnick from the Academies of Loudoun in Leesburg, Virginia, and I've created the first self-replicating machine in the form of a fully 3D printed 3D printer. The self-replicating machine has a number of applications which will revolutionize human industry, but I've chosen to highlight the 3 most impactful here. First is a self-replicating terrestrial factory. These can be deployed anywhere on Earth to bring modern manufacturing technologies to remote regions. Since these factories can autonomously build themselves, they can also autonomously upgrade themselves, meaning the newest technologies can be implemented in the field with minimal factory downtime. Since these factories can exponentially grow their production capacity through the process of self-replication, they can quickly react to spikes in demand and prevent shortages of critically needed equipment. Moving on to the second application, the self-replicating space probe, these dramatically increase our access to space, as only one spacecraft must be built and launched from Earth, but through the process of self-replication can result in thousands and even potentially millions of spacecraft all over the galaxy. Since space is so large and it takes so long to get anywhere, spacecraft could become obsolete by the time they reach their destination. But with the self-replicating spacecraft, the newest technologies and scientific instruments can be applied to the entire fleet of spacecrafts at essentially the speed of light, since these spacecrafts again can build themselves. Finally, the self-replicating lunar factory is a combination of the previous 2 applications. Since there are minimal land restrictions on the moon like there would be on Earth, these factories can truly grow exponentially. Additionally, the low cosine losses and no drag losses when launching spacecraft from the moon mean that we can very efficiently mass produce spacecraft on the moon and launch them into Earth orbit or beyond at virtually no cost to Earth. One type of satellite that we could produce on the moon is a solar power satellite. These can provide almost limitless clean energy to Earth at virtually no cost to Earth, which resolves our dependence on fossil fuels. Now, all of these applications are very interesting and very impactful, but the self-replicating machine is very difficult to build. I've identified 3 critical characteristics a self-replicating machine must have in order to achieve those applications. First is self-manufacture. The machine must have the ability to create every part in its duplicate from a raw feedstock. The second is self-assembly. The machine must assemble those manufactured parts into a new functional duplicate. And finally, universality. The machine must have the ability to make more useful parts than just its duplicate, which is what allows it to be a spacecraft, a factory, or really anything else. The purpose of my project was to create the first proof of concept of an autonomous self-replicating machine in the form of a fully 3D printed print-in-place 3D printer, which satisfies all of those requirements. There were, however, 4 critical problems I had to solve in order to achieve that goal. First, we don't have a highly conductive 3D printable material with which to print electronics and motors for the printer. Problems 2 and 3 are related. All 3D printers today use microprocessors, but these microprocessors are impossible to 3D print. So a method of controlling the motors of the printer without using microprocessors, which is problem 2, and a method of storing a digital model to be printed, which is problem 3, again, without using microprocessors, must be developed. Finally, the hot end of the 3D printer must be able to print a duplicate of itself without melting in the process, which is impossible for common 3D printing materials to do. And the kinematic system, or the frame and motion system of the printer, must be fully 3D printed as well as fully print in place, meaning it's printed all in one piece and does not require any assembly to be functional, which is how this machine satisfies the self-assembly requirement. I've solved all 4 of these problems and will step through my solutions now, starting with the conductive material, which is shown here. My conductive material is 98.3% less resistive than the best commercial alternative material. The material is made by extruding a low melting point solder paste alloy through a 3D printed paste extruder onto a 3D printed substrate. The material is then sintered, whereby the individual solder particles are melted together to form a solid continuous trace. This process is actually quite difficult as the molten solder likes to bead up instead of lay in long continuous traces, which is not optimal for this application. So to make this process work as consistently as possible, I've created over 70 individual electromagnetic coil prototypes in order, again, to make that process as consistent as possible. From these electromagnetic coils, I've created the first fully 3D printed brush DC motor, which is animated here. This is a 3-pole brush DC motor. It draws 8.5 amps at 30 volts and spins at over 1800 RPM, which is sufficient for the final printer. The low electromagnetic turn count of each of the electromagnetic coils within this motor do limit the torque of the motor, but this is compensated for in other parts of the design. Moving on to problem 2, which is the motor controller. The motor controller uses 37 compliant conductive arms, one of which is shown here, to read a data strip. This data strip also has 37 channels, or the vertical columns here. And if there's a gap or a hole in each of these columns, this conductive arm can fall through and make contact with the conductive pads below. This is how the motor controller sends signals to the motors controlling the motion of the printer. To actually generate these data strips from a digital model, I created a custom converter program which uses a 7-step process to encode a digital model into a representative data strip. The digital model that this program reads is called a G-code file, which is a series of movement vectors which the printer follows in series in order to trace out the part being printed. For each of these movement vectors in 3D space, I split them into a normalized heading vector, which is essentially the direction in which the printer should move, and a scalar movement duration, which is essentially for how long the printer should move in that direction in order to recreate this original movement vector. For each movement vector in that original G-code file, a single row on the data strip is allocated, where the distribution of activated and inactivated channels in this data strip row encodes the normalized heading vector, and the height of each of these rows encodes how the scalar movement duration, how long the printer should move in that direction. Since the printer can only move in 250 million unique directions because of the limited number of channels, the heading vector must be approximated as it's encoded into the data strip, which results in errors in this encoding process. Here, the original model is shown next to the model which has been reconstructed from a data strip after it's been encoded. And this error is unacceptable. So I've implemented two machine learning techniques to reduce this error, the first of which is a gradient descent algorithm. Again, since the movement vector, which is encoded in the original G-code file, will be different, slightly different than the movement vector that's encoded in the actual data strip, there will be some discrepancy between the intended final point of the hot-end and the actual final point, which is shown here by this red dashed line. To minimize this error, I've created this gradient function, this cost function, which has been derived from the Pythagorean theorem. And when the gradient of that, or the derivative with respect to the movement duration, is repeatedly applied to each of these movement vectors, that error is moved towards the local minimum of this cost function, or the optimal value for the movement duration. This gradient descent optimizer reduces error significantly. Here, the model is recognizable, but there are still imperfections which are completely removed by this second machine learning technique, a genetic algorithm. This, instead of optimizing the data strip itself, this actually optimizes the value of each potentiometer on the motor controller. If these potentiometers are left unoptimized, the motors can spin at more fast speeds and fewer slower speeds, which means that the distribution of heading vectors, again, directions in which the printer can move, is not evenly distributed. So if the printer wanted to move in this direction, for instance, you'd have to approximate that as one of these nearest heading vectors, which introduces a lot of error in the print. After this genetic algorithm is run and these resistances are optimized, this distribution of heading vectors is much more uniform, and error is reduced to a point where the encoding is almost perfect. Both of these machine learning techniques reduce error by 99.999% in this final data strip here. After the encoding process, the data strip is exported to be 3D printed. Since normal 3D printers cannot print the entire data strip in one piece, since they can be several meters long, I've designed and built this custom 3D printer which prints onto a conveyor belt in order to print data strips of any length. Finally, we come to problem 4, the final problem for this printer. Starting with the hot end is fully 3D printed from a polymer called PEEK, or polyether ether ketone. This polymer can be annealed after 3D printing, which raises its continuous use temperature by 120 degrees Celsius, which could allow it to print itself. Since this material is printed at a much higher temperature than standard 3D printing materials, I built a second custom 3D printer. This one is water-cooled and within a heated chamber in order to achieve those high printing temperatures. This hot end was successful. Here we can see it has extruded some PLA plastic on the build plate. PLA plastic is used to print about 95% of the machine, so that's a very good sign. The extrusion inconsistency problems here will be solved by a third version of this design, which I am currently designing now. Finally, the kinematic system is the frame and the motion system of the printer. This has been designed to be fully print in place, meaning it is printed in one piece and does not require any assembly. Here, it's still sitting on the print bed after being printed. All of the bits, components are there, and the moving parts have to be snapped apart to reach this final functional design. This is exciting in its own right, as for the first time, we can print about 80% of a 3D printer in less than a day and for about $5 worth of material. Finally, all of these components have been combined in a final proof of concept. Here, this data strip is being read by the motor controller, and that's that's controlling this fully 3D printed motor, which is moving in axis on the kinematics. Finally, on to the conclusions. This machine is the first assist self-replicating machine, which means it's the first machine to satisfy universality and self-manufacture. This is capable of achieving any of the applications set forth in this presentation if the human is there to assemble the printer. More importantly, though, this is the first proof of concept of an autonomous self-replicating machine, which means it demonstrates technologies required to fully satisfy all three of these criteria. This is very important, as before this project, it was estimated that the technology required to build an autonomous self-replicating machine would only become available within the next few hundred years. But after this project, I believe it's available within the next 10 years, and I'm actively working on extending my project to complete self-assembly and make that a possibility. Finally, I'd like to thank my project mentor, Mr. Chapin, for helping me in the presentation of this work, particularly this presentation and the associated published paper. Thank you very much.
Hi, my name is Michelle Hua, and I'm a 10th grader from Cranbrook Kingswood Upper School in Michigan. Today, I'll be talking about my work, the Dilated Silhouette Convolutional Neural Network for Human Action Recognition. So recognizing and analyzing human action is very important in many real-world applications. For example, ensuring public safety by spotting dangerous behavior, analyzing sports, improving autonomous driving, coaching, and assisting with physical therapy. Due to the current pandemic, people have limited access to public facilities such as gyms and physical therapy clinics. This is where AI-based action recognition can greatly benefit society. These algorithms are convenient and can facilitate tasks like coaching in sports and physical therapy because they can recognize and analyze action. However, using AI to recognize actions poses numerous challenges since human actions are complex sequences that contain information in both 3D space and a long time. Current AI algorithms struggle with analyzing both pieces of information. So, this is what led me to think of whether there's a better representation of action in space and time and a better framework for recognition, which is what I investigated in my research project. Currently, one method to recognize human action is to use 3D depth cameras such as Microsoft Kinect. However, these specialized cameras are not common, which severely limits their feasibility in real-world applications. Nowadays, regular RGB cameras, such as our phone cameras, webcams, etc., are more readily available. So, using these cameras for action recognition will have bigger impacts. Currently, there are two categories of existing algorithms that use RGB videos as inputs. Image-based methods use information from pixels in image frames of a video to recognize action. However, these methods need large amounts of training data to accurately recognize action, and they have a high computational cost. Another method is geometry-based, and they compute geometric features like the human skeleton as a stepping stone to help recognize action. But the process of estimating the human skeleton is error-prone and may result in an inaccurate action classification. I conducted my preliminary study and created an iOS app that uses a skeleton-based action recognition algorithm to analyze videos and provide real-time coaching for users. Worth mentioning, my app was the Congressional App Challenge winner this year. Through my app, I observed that mistakes are often made when computing the skeleton. So action recognition using these erroneous skeletons will be inaccurate. This led me to think of using silhouettes, as shown in red, as geometrical representations of human action because they are easy to compute, contain enough discriminative information to differentiate between action, and are more robust. Even in a dimly lit environment with a complex background, the human silhouettes are still very accurate and a good representation of human action. In some cases, silhouettes are better representations of action than the human skeleton. For example, in this video, if we were to compute the skeleton of this person jumping, it will likely be incorrect when the person leaves the frame because his entire upper body is missing. However, the silhouettes are able to capture the remaining portions of the body that are inside the frame to accurately represent the action that's occurring. With my novel idea of using silhouettes to represent action, I designed a novel dilated silhouette convolutional neural network to perform action recognition. The first step is silhouette extraction. Human silhouettes are extracted through a modified mask RCNN algorithm. The algorithm only detects humans and finds the silhouette boundaries around humans. As seen in this picture, the human silhouettes are accurately computed through a foreground-background separation. Silhouettes are efficient to compute and are very robust because they don't require high-level knowledge about human anatomy. Next, I form my stacked silhouette point representation. Silhouettes from each frame are stacked next to each other to form a dense 3D volume with many points that make up the silhouettes. Each of these blue points have X, Y, and Z coordinates to represent their location in 3D space, with Z being the time axis. These points are then downsampled through the farthest point sampling algorithm. The new point cloud has fewer points to reduce the computational cost and serves to normalize the data to account for different video lengths. The point cloud then enters my dilated silhouette convolutional neural network. To extract features for action recognition, I need to perform convolutions on my point clouds. Traditional 2D pixel-based convolutions are typically performed on images with fixed pixel positions on a grid. So fixed convolution kernels can be ran as shown in this video. However, on my 3D point clouds that are irregularly sampled, traditional convolutions cannot be applied. Instead, point convolutions have to be approximated with a nonlinear function within a local neighborhood. Here's my dilated point convolution formula. First, the k nearest number of neighbor points in a specific point's local neighborhood are found. Here, delta x, delta y, and delta z are the local coordinates of the k nearest neighbor points. F here is the feature that you'd like to use. For example, I use the coordinate locations, but you can also use the normal value or tangent value of points. T is a dilation across time to allow SCNN to see a wider range of silhouette shapes. W is the weight function, and S is the inverse density function to make sure that all points in an area are equally accounted for. I then use multilayer perceptrons to compute the weight and density functions from the training data. Here's my unique dilated point convolution on a local neighborhood in practice. I use two 1x1 convolutions and a rectified linear activation function to configure the multilayer perceptron so that I can use the PyTorch framework to implement it. Through this MLP, the weight function is computed. The process is the same for approximating the density coefficients. After multiplying the weights and the density coefficients with the input values, a feature map is obtained. Here's the overall design of my SCNN. The input is a list of 4,096 points in the point cloud representation of an action video. It goes through my novel dilated point convolution layer, which performs convolutions on the points in the input to get a feature map. Next is the pooling layer to downsample the number of points by 1/4. Followed by another dilated point convolution layer and a multilayer perceptron, my SCNN obtains the output feature vector. SCNN is unique because it is one of the first algorithms to define a dilated point convolution neural network for action recognition. I also designed and implemented a slow-to-fast network that performs dilated point convolutions on different sets of silhouettes. These three branches of my SCNN help it to see both big and small changes in silhouettes through time, therefore resulting in a more accurate action recognition. Finally, I use fully connected layers and a softmax function to classify the action. I trained and tested my SCNN on the HMDB, JHMDB, and UCF101 datasets. I also compare SCNN to state-of-the-art methods, visualize per-class accuracy, and conduct ablation studies. Compared with state-of-the-art geometry-based methods, SCNN has the best performance on the three benchmark datasets, as shown here. SCNN is the best complement to pixel-based methods such as i3D. When SCNN is integrated with i3D, the best accuracy is achieved out of all other algorithms. SCNN performs especially well when the training data is limited, which is important for many real-world applications where it may be costly or difficult to obtain large amounts of training samples. Here's a graph that shows SCNN compared to the pixel-based method i3D in terms of accuracy per action class. i3D is currently the most accurate pixel-based action recognition method, but it has a high computational cost. On the other hand, my SCNN has a fast computation due to its sparse silhouette representation. As seen in my graph, SCNN has a higher accuracy than i3D in all of these actions where the silhouette point representation of action is helpful in capturing the change of shape motion over time. A current limitation of my algorithm is that it slightly underperforms in analyzing motion that significantly involves objects such as throwing or shooting a ball. However, this challenge can be alleviated by recognizing objects, finding their silhouettes, and analyzing object motion in the same way that SCNN does for humans. I also conducted ablation studies to demonstrate the importance of SCNN's slow-to-fast network and time dilations. Without these two parts, SCNN's accuracy drops about 1 to 2% as shown in these two tables. SCNN also offers an improvement in the length of training time required. It only takes 3 hours to complete training, whereas the Potion and I3D algorithms required 4 and 9 hours of training time, respectively. In conclusion, here are my main contributions. SCNN uses the novel stacked silhouette point representation to explore information contained in the 3D space and time of human action. SCNN computes dilated silhouette point convolutions that yield distinctive geometric features for accurate action recognition. SCNN outperforms all other geometry-based methods. When combined with I3D, SCNN achieves the best performance out of all other algorithms. I further implemented SCNN in my iOS app to recognize complex actions and provide real-time coaching in fitness and physical therapy for users. Here's a video of SCNN functioning in my app. SCNN computes human silhouettes in real time and overlays it on top of the user in a red outline. My algorithm recognizes the action and displays the action class on the top of the screen, as seen here. I would like to thank Professor Zichun Zhong from Wayne State University for guiding me through this process and providing valuable feedback. Finally, here are my references. Thank you to the SMART Scholarship for inviting me to present.
Hi everyone, my name is Ishani Shah and I'm an incoming freshman at the University of California, Berkeley. The title of my project is Doped Biochar for the removal of pesticides, emerging contaminants, and heavy metals from water. Water contamination is a key challenge of modern civilization. In fact, according to the World Health Organization, nearly 2.1 billion people worldwide lack access to clean water, and 80% of wastewater is disposed without proper treatment. Moreover, the percentage of water available as drinking water to us is significantly lower than the total percentage of water on Earth. Current water contaminants include 3 major classes: pesticides, especially organochlorine pesticides such as PPDDT and PPDDE, emerging contaminants such as pharmaceuticals and microplastics like BPA and dimetrodazole, and inorganic contaminants like heavy metals, arsenic, lead, mercury, and cadmium. So my goal was to design a highly efficient, sustainable, and affordable water purification system for the rapid removal of pesticides, emerging contaminants, and heavy metals from water. With this goal in mind, I decided to use biochar as my base filtration material. Biochar is a carbon matrix made from the thermochemical pyrolyzation of initial biological feedstock, which makes it like activated carbon. However, it also has added functionalities due to properties of the initial feedstock, which gives it an advantage over activated carbon. And chemical surface modifications can enhance the uptake of pollutants and allow for better selectivity. The chemical surface modifications I used were manganese oxide, zinc oxide, and thiols. In total, I engineered 6 different kinds of biochar to test the effectiveness of biochar for the removal of certain pollutants. For example, I engineered manganese oxide thiol-doped milled rice husk biochar, and then I compared it to thiol-doped rice husk biochar to determine the effect of catalyst presence on the removal of contaminants. Similarly, I compared other types of biochar to determine the effects of surface area, complexing agent presence, pore size, and finally, carbon content on the effectiveness of contaminant removal. To engineer my biochar, I first created 200 millimolar solutions of chemical modifications, then added the initial feedstock, so either rice husk or oak wood, to the solution, and then pyrolyzed it in a vertical tube furnace. I then allowed the biochar to dry for 72 hours. For manganese oxide modification, I used manganese chloride. For zinc oxide modification, I used zinc chloride, and for a thiol modification, I used cysteine. I then analyzed the surface of the biochars using X-ray absorption near edge structures. And here you can see the sulfur zanes for enhanced biochar, from which we can see that cysteine was the primary sulfur species functionalized to the surface of sulfur-doped biochars. Similarly, for zinc stains, we can see that zinc oxide was the predominant zinc species functionalized. And lastly, for manganese stains, we can see that beta manganese oxide or pyrolusite was the predominant manganese species functionalized. This tells us that the biochar doping was successful. Next, to test the biochar, I first prepared 100 micromolar solutions of my organic contaminants, so PPDDT, PPDDE, dimetrodazole, and BPA. I then placed the biochar in the solution and then removed it via filtration in 10 minutes. I then analyzed the filtrate using gas chromatography mass spectrometry. Similarly, for inorganic contaminants, I prepared 100 micromolar solutions and then added arsenic, lead, mercury, and cadmium of those concentrations, placed the biochar in the solution, and then removed it from the solution via filtration in 10 minutes. I then analyzed the filtrate using ICP-MS analysis. Here you can see my results, and as you can see here, manganese oxide thiol-doped milled rice husk biochar appears to be significantly more effective than other biochar types at contaminant sequestration. Again, for heavy metals, the same trend applies. Manganese oxide thiol-doped milled rice husk biochar appears to be very effective. For organochlorines, manganese oxide thiol-doped biochar was the most effective, removing 98.31% of PPDDT. This tells us that high surface area, catalyst presence, decreased pore size, complexing agent presence, and increased percent carbon composition are key for contaminant sequestration. Moreover, 12.54% more PPDDT was removed by manganese oxide thiol-doped milled rice husk biochar versus unmilled rice husk biochar, which tells us that high surface area is key for PPDDT removal. Also, catalyst presence is key because 7.02% more PPDDT was removed by manganese oxide thiol-doped biochar versus just thiol-doped biochar. From this, we can see the proposed reaction mechanism might be dechlorination of the peripheral chlorines. Cysteine and PPDDT would interact, and one of the chlorines would replace the hydrogen group on the thiol. This is also in line with an average of 5.78% less PPDDE removed across all types of biochar compared to PPDDT. PPDDE has one less peripheral chlorine, so it makes sense that the less chlorine there is, the less likely it is for this reaction to occur. This proposed reaction mechanism could further be used to sequester other more deleterious organochlorines as well, such as dieldrin and heptachlor. Next, let's look at dimetrodazole. Manganese oxide thiol-doped milled rice husk biochar was again the most effective for dimetrodazole, removing 53.34% of contaminants. This tells us that high surface area, catalyst presence, a surface complexing agent presence, increased percent carbon composition, and increased pore size are important for the sequestration of antibiotics. Now, this is a little interesting because here, pore size was actually the most important for contaminant sequestration, and 29.19% more dimetrodazole was removed by zinc oxide thiol-doped biochar versus just thiol-doped biochar. And another very interesting data about dimetrodazole was that the percent of contaminants removed was actually negative for this. Now, this requires additional explanation for the undoped rice husk biochar data. Negative 1.55% was removed. This would lead us to two conclusions. Either dimetrodazole was produced as a result of filtration, but this doesn't make sense for our data because it was not pre-existent in the matrix solution, which was effluent from the biochar pre-wash. So we know that dimetrodazole was not produced as a result of filtration. A more plausible explanation is that the amount removed was actually 0%. Thus, the error of the GCMS instrument is 1.55%, which falls under the 2% error bar from standard deviation. Next, let's look at BPA. For BPA, zinc oxide thiol-doped rice husk biochar was the most effective for contaminant sequestration. Zinc oxide thiol-doped rice husk biochar removed 96.49% of contaminants, and high surface area, catalyst presence, decreased pore size, increased percent carbon composition, and complexing agent presence were key for contaminant sequestration. But we see here that complexing agent presence was by far the most important for effective sequestration, and 9.46% more BPA was removed by thiol-doped biochar versus undoped biochar. Here, our proposed reaction mechanism is adsorption by thiols. BPA is a planar molecule composed of carbon rings. This allows for carbon pi bonds in the electron cloud rings above and below the molecule. Thiol-pi interactions would allow for the sequestration of BPA. Now let's look at heavy metals. Manganese oxide thiol-doped milled rice husk biochar was by far the most effective, removing 97.78% of arsenic, 98.23% of lead, and 100% of mercury and cadmium. However, there was no statistical difference in the data between surface area, catalyst presence, and pore size. However, there was a significant difference between thiol-doped rice husk biochar versus undoped rice husk biochar. Thiol-doped biochar removed 41.29% more of heavy metals on the average. This tells us that complexing agent presence is key for heavy metal sequestration. Similarly, increased carbon composition resulted in 5.34% more heavy metals removed. Now, looking at the percent of heavy metals removed by thiol-doped biochar, we can conclude that the proposed reaction mechanism likely involves adsorption by thiols. This would be very similar to the previous reaction mechanism we had seen. Some limitations of my research are that I only conducted 3 trials per biochar and contaminant type. More trials were beyond the scope of my research due to difficult and expensive ICP-MS and GC-MS testing. However, more trials would have resulted in higher confidence. The reaction was also much faster than I had expected, so I have very low resolution for the reaction kinetics. My prediction is that these are mostly pseudo-second order reactions. In the future, I hope to explore the effects of other composition parameters on biochar sequestration efficiencies, such as percent oxygen composition and percent nitrogen composition. I also hope to design a filter for rigorous testing. I'd like to thank my mentors at the Illinois Institute of Technology, Professor Bhupesh Mishra, and at the University of California, Irvine, Dr. Felix Grun, for aiding me throughout my research and providing me lab facilities. Thank you very much.